Yeah, welcome everybody. So I think this is the 18th Cardamom Seminar. Yeah, we'd like to welcome Goswami today. He finished his PhD very recently in the University of Galway. He did a great job. His thesis was called Unsupervised Deep Representation Learning for Low-Resource Languages and Applications, and I think he will be talking on that topic today as well. Koustava is now working as a research scientist at Adobe Research Lab in India. And in that context, we very much hope that there might be scope for collaboration in the future between Adobe and maybe the Insight Center at the University of Galway. So yeah, I think this talk could be the start of an interesting collaboration. And I'm sure you're all very interested to hear what Koustava has to present on today. So his title of today's talk is Multilingual Sentence Embeddings for Low Resource Languages. So the floor is all yours, Koustava.
Great. First, I will share the screen. So can you see the screen?
Yep.
Perfect. Okay. Yeah. So first of all, thanks, Doris, and everyone. Most of the people know me, but those who don't know me, first of all, like it's my pleasure to be here, which we started some years back. I'm here to present for my work here now, which is a very great thing for me. So my name is Koustava. I am a research scientist at Adobe Research India, Bangalore. I'm a part of content intelligence and natural language processing team here in Adobe. We are working on different kind of document representation learning intelligence, including pictures and different kind of languages. My journey started here. My research journey started here at Insight Center, University of Galway, under Dr. John McRae and Doris. I recently defended my thesis. So today I'm going to present my works on building efficient multilingual sentence summary frameworks which solve diverse problems in low resource natural language processing or natural language understanding domains. This is very much in the application side as well as research side. Like in application wise, I know some of my works are already been taken by one or two companies who are now working on the very the kind of applications that I built. And on research side, we tried to build some of the applications on top of what I built previously. So now I will straight jump into the research talk. During my research talk, I will start with the definition, my motivation behind the works on sentence-based representation learning, and kind of research questions that can be arised, and then the contributions that we made. So first of all, what is sentence representation, or what is sentence representation? Basically, the sentence representation learning is called sentence embeddings. So sentence embeddings is a dense vector representation of different kind of sentences. In the single vector space, similar sentences should have close representations. An example of the same is given in the right-hand side picture. If you see the right-hand side picture, there is an embedding methodology, and we say that there is a vector representation out of it that we call sentence embedding, but it is actually the sentence representation that we are learning out of different kind of text corpus. It can be unlabeled text corpus, it can be labeled text corpus. Sentence embedding in today's era plays a big role in different kind of natural language processing tasks, including different kind of question answering tasks, different kind of different kind of natural language understanding tasks, different kind, even in case of Adobe, when we are talking about Adobe, we think of like Acrobat Reader. Acrobat Reader has different kind of documents. So when we say sentence embedding, documents have different kind of sentences or words, and different kind of words from the granularity level will make the sentence. So different kind of document understanding also has this kind of sentence embedding. So what happens if we talk about more about the monolingual setting? So in case of monolingual settings, the sentences when have a different kind of from a different kind of language, a single language, we say it is a monolingual sentence embedding. But what happens if we talk more about like more and more of languages, then the monolingual setting? If you know, in Google, they are working in a project which is called no language far behind. If in Adobe, we are also going towards the direction that we will be talking about all the languages that is present, and we will be working with all the languages because documents have different kind of languages or images when we talk about the representation learning. So what is multilingual learning? So basically that is when the multilingual sentence embedding techniques comes into picture. It efficiently maps the multilingual text into the single vector space. As you can see in the right hand side picture, sentences which carry the same meaning in different languages are very close in a single vector space, and that is called cross-lingual sentence embedding representation. This has huge significance in NLP tasks, as there are more than 7,000 languages exist in the universe. And NLP applications actually have gone beyond the high resource languages like English, German, Chinese for different kind of intent classification, personal digital assistance, search information retrieval, even the kind of work that you can think of from Adobe like image captioning, image editing. In those cases also, if you take the sentences into account, those are now going into the multilingual dimension. Like if you see the image, a image can be captioned by a German sentence, it can be captioned by a Hindi sentence, it can be captioned by a South African sentence. So we have to deal with this kind of sentences when we are talking about multilinguality. Otherwise, only with English, the applications will be very narrow down. So the companies are actually going to work with this multilingual things very rapidly, very aggressively. So when we talk about this multilinguality, there are basically some of the state-of-the-art unsupervised and supervised sentence embedding methods available. So when we talk about the unsupervised methods are mostly based on the language models where the CLS token or the mean pooling of the last layer is considered as sentence embedding. But this method has a very limited capacity for understanding semantic relatedness among the sentence pairs. On the other hand, if you see the supervised sentence embeddings like laser or multilingual lacebird, is shown to perform well on NLU tasks. Different kind of NLU task has been performed using this multilingual lacebird or laser. Like if you see the different kind of startups that are coming out like Cohere or some of the models that has been deployed by the Hugging Face, they are working explicitly with this multilingual lacebird kind of models or labs models, and they are actually performing quite well on the NLU tasks. But the main disadvantages of these models are they heavily rely on the parallel training datasets for training, and it is less efficient when it comes to low resource languages or under resource languages. Also, in case of NLU tasks, though these sentence embedding methods perform well in terms of natural language understanding, large between language models like XLMR, XLMR-XL are more effective in capturing semantic information and understanding due to their embedding dimensionality and generic pre-training. But the main disadvantage of using these models are fine-tuning these large language models on domain-specific datasets require huge computation memory. Moreover, in industrial settings, it is not always possible to deploy these big fine-tuned systems in small-scale environments. I can give one example, recent example. So we were trying to understand how to encode this kind of diffusion models using this kind of distilled models as well. So we were trying this kind of diffusion distilled models to be deployed in a single GPU system. So when we talk about training in a research environment, we talk about multiple GPUs, like just take multiple GPUs and do the research work. But in case of industrialized settings, it's not always possible to enforce the systems in the multiple GPUs. So in case of industrial settings, there is a huge push to deploy the systems in a single GPU or CPUs. So our work actually tries to bridge that gap and see whether we can build the systems in a smaller environment and can be deployed in a smaller environment rather than having big language models every time. So this boils down to two research questions. Can we design an unsupervised deep sentence embedding framework to produce efficient sentence embeddings in cross-lingual domains for low resource scenarios? And how to enrich cross-lingual semantic understanding of sentence embedding frameworks to produce comparative result with lesser training and resource requirements. So for the first research question of producing unsupervised multilingual sentence embedding, we have come up with a novel idea of a dual encoder based unsupervised and weakly supervised sentence embedding framework, which bridges the gap between efficient sentence embedding generation for low resource languages, as well as produces state-of-the-art unsupervised results on high resource languages on different NLP tasks. We introduced an anchor learner machine learning framework, which has been taken by different communities now. And we also propose an unsupervised loss function that considers word mover distance as an anchor element while training the model. We presented this paper in NLP main conference 2021 as an oral distribution. For the second research question of better semantic understanding in NLU tasks, we designed a novel idea called MUFIN framework, which successfully bridged the classification performance gap between sentence embeddings and the language models. We introduced a novel methodology based on the combination of unsupervised up projection, sentence embedding alignment to domain specificity, and meta embeddings to capture the knowledge of large language models and sentence embeddings within a single representation. So MUFIN takes less time and memory to be aligned with in-domain datasets. When we say in-domain, it can be metallurgical domain, it can be clinical domain, it can be actually the domains which we haven't seen that much in the web, like food domain or something like this. And it makes more practical. These models are getting more practical to be deployed in the industrial settings when we talk about single GPU. So this paper is actually published in IEEE Big Data 2021 main conference as a oral distribution paper. So I'll demonstrate the contribution towards the first research question, which we call DuEAM. So we introduced dual encoder with anchor model trained in a multitask setup. The learner module is trained to generate sentence embeddings such that the Euclidean distance between the learned sentence embeddings closely approximate the WMD, which is the word mover distance, calculated using token embeddings by anchor between the sentence pairs. As you can see in the loss function, we use word level semantic knowledge from the pre-trained multilingual language models in the anchor model to gauge the semantic similarity between the source SI and target TI sentences. You can see in the right hand side picture, I have given an example. So the German sentence and the English sentence is there. And so the source sentence is English, which is SI, and the target sentence is TI. Subsequently, embeddings for SI dash and TI dash, which are actually getting generated by the learner such that their vector space distances reflect their degree of semantic relatedness. This tends to preserve the relative semantic distance between the input sentences, enabling DuEAM to capture the semantic relation at the word level within the sentence embeddings obtained. Forcing the system to consider the knowledge of our anchor system about the semantic relationships of the sentence at the word level helps to stabilize this training process as the pre-trained anchor model is fixed and the WMD score is considered as a scalar. So the idea and the novel idea behind this is during the backpropagation, this loss function is fully differentiable. We can differentiate the loss function, and gauging the scalar function doesn't hamper the backpropagation during the training process. So now on the other hand, while mapping the semantic similarity sentences close to each other in the shared vector space, an effective embedding framework should also address the translation ranking problem to efficiently map correct translation of the source target sentence pairs within a compact zone of the vector space. Since our methodology, which is called DuEAM, is an unsupervised approach, we introduce the translation mining based loss using the cosine similarity score between the source and the target sentences to handle the translation mining. And then what we do is we train the model using a multitask setup using these two loss functions, LA and LB. Now, so we have given an high level overview how this is happening, but why this is happening. So I have tried to give an I have tried to give a mathematical intuition as well as some kind of linguistic intuition behind this. So in this slide, I will explain the mathematical intuition behind the designing of a loss function. In the case of unsupervised learning, the main problem lies in the case of model stability. In learning that, there is a huge possibility of divergence because the problem of the entropy is there. So the calculation of the entropy is very hard because there is no y, so there is no label, or the true, or we say true dependency is not there. So we have introduced the exponential unit in the loss function, which forces the system to be in the positive range and in a very stiff boundary range. If you see the right hand side picture, I have given the gradient distribution diagram here to show how this is actually happening. If you see the diagram, the gradient distribution is very stiff. So the boundary is very stiff. So the oscillation is actually happening between the 0 to 1 range. This also forces the system to be more stable as the gradient oscillation is very less. The effect of our inclusion of word mover distance at the time of backpropagation can be explained with some very easy mathematical intuitions. So I've given some of the intuition here. If you see the mathematical intuition that I have given downward is like, first example, if word mover distance is high, but the Euclidean distance is 0, generally the model without our word mover distance will think that, okay, the convergence have happened, so that sentence pairs will have a perfect similarity. But when we are introducing the word mover distance, the loss value produced by the system is high, which semantically right as the sentences should be kept apart in the vector space. In the real world scenario, which is the third example, we can see that the loss function is 0 when the word mover distance and the Euclidean distance both are 0. So the mathematical intuition behind our newly designed loss function is self-explainable, and it is correctly providing the semantic information while the learner generates the embedding. But what are the advantages of our proposed approach on sentence level linguistically? Here are some of the examples. By using WMD, DuEAM generates closer representation for similar sentences, while at the same time forcing the dissimilar sentences to have embeddings that are apart in the vector space. This provides better semantic understanding for improved performance in downstream tasks as observed in our experiments. Also, the model is able to capture the negation and other semantic information for better performance, which is very important when we are talking about the vector space representation either in word level or semantic level. For example, the WMD between the German sentence mentioned in orange, which is the negative sentence, and the English sentence, she is a teacher, is more than the between the German sentence mentioned in green and the English sentence, she is a teacher. So if you see the example, negation sentence with the positive sentence should be apart, and the positive sentence of German and English should be closer together, and that we are getting from the WMD. And thus gauging this WMD information in the loss function actually helping the model to understand which are the sentences that should be near to each other in the vector space linguistically and which sentences should be apart from each other. So thus the embeddings are actually different and effectively handled by the model. Training is very simple. So for dataset, we train the model using the multilingual natural language inference dataset. For unsupervised learning, we have randomly shuffled the dataset so that there will be no dependencies between the sentence pairs. For weakly supervised learning, monolingual sentence pairs are unchanged. For cross-lingual dataset building, we keep the premises of the source language and replace the hypothesis with the target language hypothesis sentences and vice versa. In both the cases, we do not use any annotated label like entailment, neutral, contradiction, which we can found in the original dataset. And there is no parallel datasets used for training. Our motivation behind making the weakly supervised model is that generating any kind of continuation dataset or paragraph is comparatively easy in multilingual cases. So we have carried out a large number of experiments, including semantic understanding to parallel sentence matching. Here you can see we evaluate our model against the STH benchmark dataset As shown in table 1, the unsupervised baseline systems based on the language models MBART and XLMR perform quite poorly, suggesting that cross-lingual sentence embeddings are not well aligned in the vector space. For cross-lingual settings, both the DuEAM model actually significantly outperform the unsupervised models, which I have given in the first part in the table, based on the rank correlation score. It is very interesting to note that DuEAM actually achieves better results compared to the supervised laser and labs approaches for both the monolingual datasets, English to English and Spanish to Spanish, and also in the cross-lingual datasets for like English to German, English to Spanish language pairs. Now it's very interesting to see this graphs. We evaluate our model performance on the Tetoiba dataset for parallel sentence matching. From the bar chart graph on the right-hand side, in well-resourced languages like German, Chinese, we observed DuEAM actually performs significantly better than state-of-the-art unsupervised approach published in 2020, with results comparable to the supervised methods SBART and laser. We also wanted to see what is the performance of our model in case of zero-shot approaches, as this helps in many low-resource scenarios. To do that, we actually have taken some under-resourced languages from different language families, and the performance is actually very, very interesting. If you see in the chart that is there in the right-hand side, we observe that for Tagalog and Irish Gaelic, both DuEAM models actually perform significantly better than supervised multilingual SBART, while for Afrikaans and Telugu is an Indian language, we achieve better accuracy for the weakly supervised model. By the way, these languages all are from different language families, including Indo-Aryan, Celtic, etc., even South African languages. These results show that even without explicit learning for different under-resourced languages, our models can robustly handle zero-shot learning across different language families for generating efficient sentence embeddings. The entire experimental results on 58 languages, we have actually given that in paper. I would request you to look at the details given in the paper to know more about the language diversity. But if you have any questions, I will be happy to discuss on that as well. So what is the performance while training with small scale datasets for different languages? This is very interesting. We actually experiment on two under-resourced languages, Georgian and Amharic. We trained DuEAM with only 20K non-parallel Spanish to Canadian and Spanish to Amharic sentence pairs, whereas the baseline supervised model laser is trained with 296K and 88K parallel sentence pairs respectively. We see that the performance, the model is actually stable and actually outperforms the laser for both Georgian and Amharic. This replicates the stability of the model while training us less amount of data set. And it's very interesting to see we are having some of the experiments later when in the recent time with some of the Adobe datasets, and we saw that this kind of stability actually helps when we talk about the low resource deployments and developments. So we have also done some of the ablation study on model stability on different types of training datasets. So more results are there in the paper. So how stable the model while training with the different types of datasets? We consider English, German, French, and Spanish languages under 3 training trainings. So one is like we have taken 25 sentences from XLNI and it has been sampled randomly. 25K parallel sentence from TED 2020, again it is sampled randomly, and 12.5K sentences from each of the datasets. As you can see in the graph, the model actually produced similar performance when trained on XLNI or on a parallel corpus alone, while a combination outperforms the other methods. So this is all about the model, DuEAM model that we have proposed, and it's fully unsupervised. Even we have also released the weakly supervised model, which was trained using the XLNI dataset, only the XLNI dataset, without using the labels that is present in the dataset. So now we will come to the second research problem and the solution, that is the MUFIN framework. So actually the MUFIN work has 4 phases. In the first phase, MUFIN performs dimensionality expansion on the fixed length sentence embeddings by projecting the pre-trained sentence embedding to the vector space of the large language models. The projection is actually performed in 2 steps. The projection is achieved with the help of a fully connected neural network via self-reconstruction of the data based on backpropagation through the simple neural network layers. An input sentence embedding SI, as you can see in the example, is passed through the neural network, which learns to output higher dimensional embedding S-I via a nonlinear transformation shown in the slides. The projected embeddings are then transferred to the same vector space as a part of our large language models by simply minimizing the mean squared loss between their sentence embeddings. This projection stage actually helps to supplement the sentence embedding from the sentence embedding model by extracting the additional semantic knowledge that we are actually getting from the large language models and represent them together in the common vector space. One of the main advantages of our framework is that this model is fully unsupervised. You can do the projection using any kind of dataset that you like, which actually eliminates the need for expensive fine-tuning or the pre-training of the large language models. So in the second phase, the projected sentence embeddings are actually aligned to the downstream application domain using the task-specific training datasets. The projected sentence embeddings are provided to another fully connected neural network with an output softmax layer, which allows to predict category probability distribution for an input embedding across the n training levels, n or m, whatever training level you have. This enables a domain adaptation and aligns the embeddings to be tuned specifically for the downstream task. In phase 3, we use the idea of the meta embedding techniques. This diversity of different sentence embedding techniques captures different aspects of the semantics and demonstrates varying degrees of success on different classes or tasks. Also, various aligned sentence encoders demonstrate complementary strengths, which upon being fused together provides improved performance, further enabling MUFIN to bridge the gap with fine-tuned large language models. To this end, we actually combine the aligned projected sentence embeddings that we have achieved from 2 different SBERT models and frozen the laser model. And here is the interesting thing: we actually chose the frozen laser model to make them to understand the generic embedding semantic knowledge, at the same time having the projected model that we are getting from the projection of the large language model embedding space. So it actually giving us a domain semantic understanding, in general domain semantic understanding, which is actually helping us to make the model more in general or generic, I would say. And in phase 4, finally, the model learns to classify the sentence reconstruction using the sentence meta-embedding, obtain the above step, and then simply you do the classification task, you do the natural language understanding task, semantic similarity task, whatever you want to do for the downstream natural language processing tasks. So we have carried out a large number of experiments on multilingual semantic understanding benchmarks. Some of the snapshots of the result I will show in this presentation. Here you can see we have tested our model on POSIX benchmark dataset, which is a multilingual paraphrase identification dataset and which is very famous. Here we can see our proposed method MUFIN has outperformed the aligned state-of-the-art sentence embedding SBERT model, as well as it has also outperformed the aligned vanilla SBERT meta-embedding model. It is very interesting to see that only using a single aligned projected SBERT model, using which has been carried out in stage 1 in our proposed framework, we are able to achieve better accuracy than our baseline sentence embedding techniques. We have also tested our performance on mixed domain datasets. The reason behind the same is to understand model efficacy on choosing semantic relations between close-related sentences. In the graph, we can see that MUFIN actually outperformed the baseline systems and produced comparable results to large pre-trained language models. Now, what happens if we add some more in-domain datasets while training? Does it actually improve the model or it overfits? This is a very common questions that I get from the research engineers, that okay, this is fine, but in an industrial setup or in a practical setup, we can get more and more data. So what will happen if we are actually fitting more and more data, whether it overfits or whether it actually forgets what actually it has learned in general setup. So what we have done is, in this slide, you can see that we actually upsample 30% data set from the natural language understanding task, and then try to understand what is the result out of it. The translation of the languages to this data is actually in-house, and we have given the same, like how we have done the in-house sampling in our paper. From the graph, we can clearly see that if we give some more data while training the model, performance actually gets better and still outperform the state-of-the-art models, which dives to the fact that MUFIN framework can easily be adapted to new, less resource domain training without using much computation power. It can be done in a single GPU. On the previous note, we also wanted to see what is the performance on the model on the less training dataset. So we have evaluated the proposed MUFIN framework on subsample data from Amazon review dataset, which is a very hard mixed domain dataset, and compared the performance with XLML large language model, because XLML large language model has been proven to be very giving the state-of-the-art results. So we have randomly picked 2000 training samples from each classes, resulting total 10,000 training samples, and tested on provided test datasets. From the graph, it can be observed that MUFIN has outperformed the large language models. Thus, the MUFIN is more efficient and easy to be trained with smaller datasets, giving the opportunity to implement for a wide range of natural language processing tasks in industrial settings. So to conclude, we have introduced DuEAM and MUFIN frameworks. DuEAM produces efficient unsupervised multilingual sentence embedding for different languages, whereas MUFIN framework actually successfully bridges the classification performance gap between sentence embeddings and the large language models. Our proposed word mover distance based unsupervised loss function in DuEAM actually captures the semantic relatedness between the sentence pairs in monolingual or multilingual setup in unsupervised way. MUFIN framework learns enhanced sentence representation geared towards sentence classification, having the knowledge of the large language models and the meta embedding techniques. And the beauty of the MUFIN is like you can actually play as a plug and play model without going to the phase 2 or phase 3. You can just do the phase 1 with a single sentence embedding framework, and you can jump to the stage 4, and you can do whatever you want to do for the downstream tasks. These frameworks actually outperform the supervised sentence embedding techniques on low resource languages and applications. Both of these frameworks are easy to extend for the low resource scenarios and also easy to be deployed in the organizational setup, as it can be done in a single GPU, as they require less computation, training, and memory. And before ending, so if you are interested to work with me in internship or collaborations in Adobe, like we are open to that. We have some of the every time we are interested to hear from the students or the professors, and the research topics that I'm very much interested in is like multimodal grounding or generation, large language model understanding, designing of generative models, representation learning using reinforcement learning or self-supervised learning to do the human feedback process, which is very famous in ChatGPT setups. And we are very much interested to see how that can be leveraged in different kind of settings in a research perspective or in a practical setup. And this is my official email address. And if you want to know more about my research, upcoming research, which is like I'm more working on the instructional learning or prompt-based learning for this kind of sentence embeddings, which has been recently accepted to EACL as well. You can email me, you can follow me in Twitter, and I'm very happy to listen more about the new research domains or directions that can be brought into account from different kind of people, either from students or professors. Yeah, so this is all from my side. And if you have any questions, I'm happy to take any questions if you have.
Great. Thank you very much. So, are there any questions in the audience? You can write them in the chat, but feel free to also, yeah, put on your camera and ask now. I think Tunde has a question, yeah? Yeah, go ahead, Tunde.
Okay, hi, thank you for your wonderful presentation. And I have a question. I just want to understand the motivation behind adopting sentence embedding for your research, especially for low resource, and under resource languages. Like I know I've heard about character embedding, word embeddings, and all other embedding forms. So what is the motivation? In what way is sentence embedding superior to all these other embedding forms? Yeah, thank you once again.
Yeah, thanks, Tunde. It's a very good question, actually. So we can see in this way. So word forms the sentence forms the document. So when we talk about this large language models, what is the best possible way to do if you think about the kind of natural language understanding kind of tasks, like the question answer generation, understanding different kind of classification, sentence similarity matching, then what is the best possible way that you can think of to leverage the word embeddings to a sentence? Because at the end of the day, you need to have the sentences to do the classification task or similarity task. You can say that, okay, I will just take the language model or any kind of character embeddings, just take the average out of it and do the classification. That's fine. But literature shows that if you think from a intrasentential or intersentential perspective, even in monolinguality or multilinguality, from a from a very old literature as well, not very old, from early works as well. Like if you see the work from Doc to Wake also gives the idea that if you think the document from a sentence point of view, it actually makes sense. Because if you think the paragraphs, the way we write is like every sentence is related. It's not that every word is related. Word is actually making the sentence, but at the end of the day, sentences are related, which actually will make sense to understand what is actually written down in the paragraph. So when you are doing the abstraction, like suppose you are doing question answer classification or summarization kind of task. So you are taking paragraphs. Paragraph has maybe 20 sentences or 25 sentences, 30 sentences. So you have to understand what is actually written in the paragraph by the sentences that is written there. And what is the link behind that? Then only you can do the summarization. That was the motivation which came into our mind, that why not exploring how to leverage the sentence embeddings better in terms of self-supervision or unsupervision, because we were very interested to we are very interested to understand what is actually going to happen for this low resource languages, because that's the challenge to work when you don't have any parallel datasets. Literature has said that when you have parallel datasets, you are fine, you can train the model. There is SBIRD, there is labs and others. But what will happen if you don't have the parallel sentences? That's where we were very interested to see what is actually going to happen if we talk about, sentence embedding techniques, learning sentence embedding techniques for low resource languages without having these parallel sentences, and whether we can actually leverage the or we can actually increase the understanding of the sentence embedding domain adaptability using the knowledge of the large pre-trained language models, because it's not every time possible to go and train language models. Like, what is the limit of that? You have PUM, you have XLMR, you have XLMR XL, you have XLMR XXL, but where is the limit? That's where our research, that's where we actually found what can be the research question and where we can actually do the research. Because in the industry setting, many companies are actually very interested to have this kind of models to be deployed in the single GPU. So that's where our motivation was behind this research.
Yeah, thank you very much for that feedback, because I learned somewhere in my previous studies that people try to capture a lot of meanings or representations in smaller chunks of tokens. Like initially they do token representations at token levels, and then in order to capture more representations, especially for words that don't exist in a vocabulary, they try to go a bit lower to subwords. Yeah, so that's why I was trying to see if there's some form of superiority of sentence embeddings as compared to subword embedding, yeah, or something like that. Yeah, so thank you for clarifying that. So my second question, if I'm permitted, sorry, moderator, am I permitted to ask?
Yeah, of course, go ahead.
Okay, thank you. So my second question is, I'm just trying to see how your research is aligned with dialogue research, because you listed as one of your research topics, your research interest, designing of generative models, large language model understandings. Yeah, so one of the areas of interest that aligns with your research topics is how to build dialogue systems in multilingual settings, because a lot of dialogue systems that we have out there are in English language and Irish languages. Like, yeah, so I think one research that is on the ground that is yet to be published, I think very soon to be published, is how to see like some form of cross-lingual dialogue systems, like where they tend to try to have dialogue systems that can take advantage of English corpus to interact in other languages. Yeah, so I can't really go deep in that research now because I didn't really study more, and they're yet to publish. So that's like one thing they're doing in dialogue space. So far, how has your research helped dialogue research? Like, in what area can dialogue research align with your research findings? Like, I'm trying to see how my research can align with yours and see if there's some form of collaboration and mentoring and all of those. Yeah, because I'm interested in dialogue systems, especially for low resource settings.
That's a very good, interesting research direction as of now, or in the current scenario, because as you know, after ChatGPT has come, it's very important to see what ChatGPT cannot do and what you can do. So I was playing with ChatGPT for last few days. Some very interesting examples I saw. So when I was saying the ChatGPT that, okay, translate, like, can you summarize a paragraph in English? It was doing. Can you translate it to Tamil? It was able to do. It was fine. But when I was trying to understand two meanings in Bengali, say chair and the Kedara, is the name, the Kedara word is actually, same word of chair. It was actually failing. That means there is still, because at the end of the day, the backbone of ChatGPT is GPT-3, GPT star, whatever, GPT 3.5 or GPT-3, whatever it is, because ChatGPT hasn't opened their paper yet. There is just a blog post. So the idea is like, when you say multilingual dialogue system, mainly what people have done is like they have, so there are 2 points. I will go one by one. The first one is where my research comes is like, you just take the DuEAM model and do whatever you want. So DuEAM is a in general sentence embedding framework trained in unsupervised way, which can be used for different kind of downstream tasks. That's number one. Number two is the MUFIN. So the idea behind the MUFIN was whether you can leverage the knowledge of the big language models and can be push into the smaller sentence embeddings, relatively smaller sentence embeddings, because SBERT was 768 dimension embeddings and XLMR Excel was 1024 and having more and more layers and attention heads. So our idea was, can we infuse the knowledge of the large language models in the sentence embeddings, smaller sentence embeddings, and you can take the idea and you can do whatever you want to do. Now, coming to your point, it's a very good research direction when you talk about the multilingual dialogue system, multilingual abstract generation and whatever it is, because in that case, you have to understand the granularities as well, not only sentence level, but also on the word level. Because the way ChatGPT is not understanding, because there are words like, which is code switch words will be there in the sentence. So it's an intersentential or intersentential. In those cases, this kind of models actually fails because it doesn't understand what is actually said on the word level. And it actually fails to understand the linguistic behavior changes. So it will be very good direction if you like, I know people are trying to understand or tackle this problem using instructional learning or prompt learning. So what you can do is like, you can just throw some prompts to understand the semantic knowledge from English and see whether that prompts can be the knowledge holder for the other languages that is there for the downstream tasks. So you are learning for English in a zero-shot setting directly for the using the transfer learning or few shot settings. You are now using those prompts as a language holder, knowledge holder, which you have learned from English, can be transferred, whether can be transferred to the other languages or not in the same language family. So that can be a very good research direction, and that can be, I will be very interested to see what is actually, what is the outcome that is coming out from this research or the experiments. So if it sounds interesting, I will be very happy to listen about the research question that you, formulate.
Yeah, thank you very much.
Any other questions? I might have one myself. I think in the beginning you said that there's a move towards using one GPU rather than GPUs in parallel. Now, I'm not that technically minded, so maybe it's an ignorant question, but why would that be more beneficial? Or
yeah, because so when you are doing inference, if you are going with the multiple GPU systems in parallel, it is number one, can be time consuming. Number two, can be financially, it can be very, it can be a big problem because GPUs are getting costlier day by day. And then infrastructure issues can be there. So companies are trying to see whether it can be fit in one GPU, then it will be cost effective, it will be faster, no need to do the parallelism, no need to do the collection of data for the collection of embeddings from a parallel perspective. So that's why there is a push whether we can go to the one GPU system. If not, then it is fine, you can go to multi GPU system, because ChatGPT cannot be played in one GPU. So if you can do that, that will be very helpful for the smaller companies to come up with their own AI systems. So that's why there is kind of push by some of the smaller companies to see whether we can leverage that one.
Anyone else wants to ask a question, or maybe not? Well, in that case, I'd like to thank Koustava for his presentation. Great to have you here again, Koustava, or at least virtually. And yeah, we're looking forward to hearing more from you, and hopefully we can get some interaction going between Inside and your place. Who knows, in terms of interns or other possibilities. So yeah,
definitely.
Okay, great.
Thanks a lot.
Thanks everyone for joining, and hope to see you in February. We will announce the speaker for February very soon.